You have fallen into a special episode of Event Horizon with John Michael Godier. In today's episode, John is joined by James Stetson, Peter Yip, and Jonathan Heinrich. James Stetson is a lead research engineer at Lockheed Martin Advanced Technologies Laboratory and serves as a technical lead and engineering program manager for multiple hypersonic defense programs and initiatives. He is an advocate for innovative, disruptive, and holistic thinking across multiple disciplines and holds several US patents. He received his BSc in Mechanical Engineering from Messiah University and has worked at Lockheed Martin for over 7 years. Peter Yip is a senior research engineer at Lockheed Martin Advanced Technology Laboratories and an aerospace and mechanics PhD candidate at the University of Minnesota with a concentration in computational physics of hypersonic flight vehicles with over 4 years of applied research and development experience for U.S. Department of Defense platforms. His current work lies in the field of dynamic behavior of materials, continuum mechanics, experimental computational physics, and hypersonic aerodynamics. He obtained his BS and MS in mechanical engineering with a concentration in mechanics of materials from the University of Central Florida and Johns Hopkins University, respectively. Dr. Jonathan Heinrich received his PhD in plasma physics from the University of Iowa in 2011. Since receiving his PhD, he has worked on a range of exciting programs that have spanned high-energy density plasma, high-power microwave sources, pulsed power, low-temperature plasma, and space weather.
James Stetson, Peter Yip, and Jonathan Heinrich, welcome to the program.
Thank you for having us.
James, I got a question to direct for you. Mach. What is Mach, and what are the rules on it?
So Mach is a dimensionless parameter, meaning that it's unitless, and it is essentially a ratio of fluid velocity to the local speed of sound in the medium that you're traveling. So it obviously varies with temperature, but in essence, if I were to say you're going Mach 0.5, you're going 50% of the speed of sound in the medium. Whereas if I were to say Mach 2.5, you're traveling 150% faster than the speed of sound in the medium.
But that changes. So can you actually apply this to, say, water? Is there a Mach for water?
There is. Water is a little bit interesting because it's a non-compressible fluid. So when you exceed the speed of sound in a fluid like water, you get what's called cavitation. And it essentially forms little bubbles, or it actually separates from your surface and cavitates.
Now, does Mach vary in altitude? So, in other words, is it a different sort of metric if you're at 60,000 feet versus 20?
No, that's actually the nice thing about Mach is the way it varies is the temperature of the air that you're flying through. So regardless of altitude, the Mach number is going to stay relatively the same.
So Mach 2 is Mach 2 in the atmosphere.
Mach 2 is Mach 2. Yes, sir.
Now, as far as actually getting up into really high speed, hypersonic speeds, you really are fighting the atmosphere, right? In that the faster you go, the more problems you have. Is that a good way to characterize it?
Very much so. From, obviously subsonic flight, that's pretty well known and established nowadays. And then you transition to what's called a transonic regime, where you have both subsonic and supersonic flow. And that's, I'm sure people have seen videos of like an F-35 or some other airplane doing really, really hard maneuvers, and you get that really cool vapor cloud that comes off the wings. Those are transonic areas, and the vapor that you see is actually called an expansion fan of the transonic regime. And then from transonic, then we obviously go to supersonic, which is by definition faster than the speed of sound in the air, which is 343 meters a second at sea level. And then beyond that, you go into what's called a hypersonic regime. But hypersonic flight is kind of a misnomer. It's merely a special regime of supersonic flight. And I'll let Peter talk to that if he would like to.
Yeah, I can touch on that. And I think I kind of wanted to circle back a little bit on the Mach number thing. Your sound speed, it doesn't matter it does matter about temperature, but it also matters about density, because at its core, it's a thermodynamic state. So every being, has some thermodynamic state, which can be expressed usually as some pressure with some relation to density and temperature. So with that being said, that speed of sound is also density dependent. So you may see some different Mach numbers at different altitudes. But the key here with hypersonics, though, is that when we talk about Mach number, it's just so convenient that these scientists before us really thought about a good way to determine different regimes of flight with this non-dimensional parameter. And so when we say we're going supersonic and we're referring to going faster than the speed of sound in air, if you keep going beyond that, there's just heightened physical phenomena that is just now makes it extremely hard to either analytically solve by pen and paper, or even computationally becomes extremely difficult. But people have thought that this Mach number really starts at Mach 5. And so I have this quote from Bill Rowe, the University of Michigan, and he gave a guest lecture at Von Karman Institute, I think 1970-ish timeframe. And so I kind of wanted to share that because I think it really embodies everything in this hypersonic regime. So bear with me when I try to rummage here and find it. Yeah, so almost everyone has their own definition of the term hypersonic. If we were to conduct something like a poll among those present and asked everyone to name a Mach number, that non-dimensional number above which the flow of a gas should be described as hypersonic, well, I think a majority of answers would be around 5 or 6, but there is totally accurate and descriptions, and someone could advocate as numbers as small as 3 or as high as 12 and defend that well. So why do I want to lay that out is that there are key physical phenomena that we care about that separate it from just typical supersonic. I think it's about 5 that I can name off the top of my head that I deal with daily. We look at the shocks that form off of a body. And I think, James, you had mentioned during the transonic regime, you'll see some of these cool images of shocks coming off. But when you're going hypersonic, that shock is near hugging your vehicle. And so you can have really thin shocks. So the actual width of the shock almost treated as this thin discontinuity. You'll have these viscous interactions. So like we think of fluids, right? Or like honey versus oil, or something that's more viscous has this higher resistance to a shear. So honey obviously takes longer to pour out, right? So it's more viscous. Well, when you're moving so fast, these viscous effects generate a flow over the body that's more close, and that's known as a boundary layer. You can think of it as this fluid that kind of just gets captured right along the surface, and it would be in between the shock that formed and then the vehicle surface. And so when the shock is so close and there's this boundary layer of fluid that's also kind of trapped in there, you end up with extremely interesting physics of heating and types of control algorithms that are required for the vehicle. So that's really important too. That is not really seen just in supersonic alone. And then the most important to me, which is kind of fun, is the high temperature effects, and then actually the gas surface chemistry that happens there that kind of separates it from supersonic. So you're flying so fast, you're potentially, depending on how fast you're going and where you are in the atmosphere, actually breaking apart the molecules, right? So you can be disassociating, ionizing these particles, and that type of vibrational excitation and all these things give rise to really complex states right at the surface. So what makes this important for me, more as on the academic side, is that the types of calculations you do, if you don't incorporate gas chemistry, I mean, you could easily be like 50% incorrect of your solution. And that's as you go into higher into re-entry velocities, as you go to like 6 kilometers a second to 12 kilometers a second. I mean, your solution, if you choose to just ignore the chemistry that's happening, your solution is extremely invalid. It just becomes more conservative if you decide to get rid of the chemistry, but we can do better now that we have more computational power and things like that. And then the one thing that we always like to talk about, space exploration, things like that. One of the things that separates the two is when you're high in atmosphere, you could be at really low densities. And so then, like James had mentioned, that can enable you to fly a lot faster. But if you're flying so high to which the molecules are now distances apart to where you can't really think of it as one continuum fluid, well, you can't use your traditional Newton laws and things like that. They tend to be very different, and things that you'd have to solve and treat are more at the molecular scale instead. And so that proves to be very difficult as well. And how you marry the two as you're descending takes a very elegant craft that is being studied today. So as you're descending, you can't just say, hey, I have a continuous fluid. That's not necessarily true. And so how you handle that is, that's kind of, people have dedicated their lives to doing that. And so some of those are main topics of why hypersonics is very unique in its sense that all of those things that I mentioned, depending on the conditions, depending on the atmosphere you're at, whatever planet you choose to be on, it could be as low as Mach 3, who knows? It could be as high as Mach 12, right? But it's these characteristics that are all coupled together really lend itself to being called hypersonic.
Now, would you characterize hypersonic as the most challenging thing in aerospace? I mean, this sounds harder than space itself as far as what you have to do to deal with the physics of this.
I might be biased because this is what I've been dedicating a lot of my time to. But I think this is the most difficult, especially because when we're talking about entering not only Earth, but different other atmospheres, when you're needing to know so much about these effects and how they couple and interact. So, and all of this is nonlinear, and I completely ignored any sort of turbulence effect, which makes it even more difficult. If we have any vision of having manned explorations onto Jupiter, into a Jovian atmosphere, I mean, that is extremely challenging to a point where it's like, it comes down to everyone needing to roll their sleeves up. We're talking about material scientists, electrical engineers, physicists alike. So I think this is an extremely difficult and the most difficult.
I would also agree on that. Hypersonics is at the very cutting edge of all of the different disciplines that Peter just mentioned there. We are very limited by materials being the biggest one, with heat dissipation, strength, rigidity, and ensuring that you have survivability, and then also reusability is a big one.
Yeah, well, that's obviously a concern within rocketry as well, is reusability and, trying to get a handle on launching something 10 times instead of once and discarding it. In regards to materials, though, let's look at the SR-71. This thing had to be built in order to expand with the heat. And these are 1950s materials. Do we still use those types of materials for these aircraft? Or do we have much better stuff now as far as being able to handle the heat of very, very rapid travel?
Well, when you're talking about the SR-71, we're still in the supersonic regime, but you're entirely right. There was a necessity to rethink the material layout of a fixed wing vehicle that's manned. So, as you said, the panels were fit loosely, and the SR-71 would actually leak fuel on the tarmac before takeoff. And the reasoning for that is, as titanium heats up, it obviously expands. And as the plane got to cruising velocities, the entire aeroshell would expand as it heated up and actually fill in those gaps, so it would no longer leak fuel, which is a good thing. And the other interesting thing, too, about the SR-71 is keeping the pilot alive. The windshield of the SR-71 was actually made out of quartz. So it was very, very good at resisting impacts, really good for heat dissipation. And the entire windshield was actually cooled by routing unburnt fuel behind the quartz panel in the titanium substructure. But as far as using titanium, it's kind of hard to replace titanium, but at the velocities that we're talking now, we need to start looking at something different. And for things like reentry or hypersonic flight, we're looking at more in the ceramics regime or carbon phenolics regime. And I can let Peter or Jonathan talk about that.
Yeah, I can comment on that. When we talk about materials, I think the most common material that, if you talk to NASA folks or anyone here, they like to talk about PICA, which is phenolic impregnated carbon ablator, right? So the idea is leveraging the fact that a material can ablate, effectively char away, can dissipate heat using the heat mechanism. And so it is kind of like a one-time use type of thing, but it effectively gets rid of the heat and therefore keeps your internal temperatures quite stable. When we talk about phenolics, that's kind of where people like to go to, and it's very low density. So that way, obviously, if it's lighter, you're kind of maximizing your range and things that you can actually safely bring your astronauts home. And then when we talk about ceramics themselves, they already tend to be in a class of heat resistance, right? And so people have been trying to come up with different techniques to generate these ceramics to also have the ability to have more deformation capability without failing and cracking. And then they still want to retain that heat resistance. And effectively, there's a whole class of materials also in metals known as refractory alloys, and there are also refractory ceramics. And so the term refractory just means it's heat resistant decomposition, right? So it can really handle these heat without decomposing. And so that's kind of this next frontier of materials, is that can we make refractories at a production level or something that's feasible for like a shuttle or something that can then be reusable to some cycle. And so that's an active area of study beyond just the typical ceramic that we use.
I was going to say, I think one more thing to think about when you think about materials for hypersonic platforms, or if you're looking any of our big challenges, right, where we have high energy densities, high enthalpy environments, right, fusion reactors, or hypersonic vehicles, or something else, right, is that these materials not only have to survive these extreme temperatures, but they need to do more for us as well, right? Dissipate heat, or have some other property that they're taking care of and have phenomenal performance there.
Just a quick go back I had just for the audience. When we say ablative heating, essentially what is happening is you're shaving off bits of this resistive material, and you can think of flakes or sparks, and that material that comes off takes the heat with it and then leaves another layer below that then does this exact same thing. So obviously you're reducing the overall thickness of the material over time, but it's a very, very good way to keep your heating in check.
So terrifying Orville Wright, in that imagine putting him in a hypersonic plane. What descends back to the Wright brothers flyer that we still have to be concerned with in our modern age of exploring hypersonic flight?
It's a great question. So obviously the basics of flight, you need to have something that has enough surface area. You need to be going fast enough in your medium to generate lift, and you need the power behind it. What the Wright brothers did is they took that philosophy and basically began a principle that we call SWAP: size, weight, and power. So as you further iterate through the SWAP process, you take what you know and you look at it and you say, how can we better this? How can we make it smaller? But we also need to make sure that it needs to fit. So say, for example, you want to launch something into space, you need to make sure that whatever you're designing is going to have to fit underneath the fairing of the missile that's going into orbit. So you need to take into account size. You need to take into account weight and weight distribution. So for Orville Wright, obviously weight is a big issue. When they made the flyer, it was made out of very, very light materials, and that was key to actually having them get off the ground for it to have sustained powered flight, as short as it was. Weight distribution, you obviously couldn't have the engine on the Wright brothers flyer all the way to the far end or the right side of the wing. It wouldn't work. So you have to look at that. And then power. How much power can you fit in that whole package while still serving and taking into account weight and size? So iteration on the swap process is how we get more powerful, smaller, and more efficient technology.
Now, about the materials again. So is there an upper limit in hypersonic flight to what we can physically produce? In other words, unobtainium or something like that, that you eventually get to a speed so fast that you don't have any material physically available to use. Is there an upper limit to hypersonic flight related to the materials that you build your plane out of?
Yeah, I think I can take that question. So if I were to be, I guess, realistic from where I stand now, I'm going to say yes, right? There is obviously physical limitations based on just the crystal structure or even amorphous structure, whatever it is, down to the atomic level of these materials will govern some of these behaviors. But people have been pretty smart in the past and will continue to be smart in the future. So I want to stand on the side of more hope that no matter what regime we get faced with, there will be interesting ingenuity for these material systems to overcome that. Like, let's say unobtainium right now is unobtainium, but 50 years from now, it has become obtainium. That's where I want to stand with that.
Well, you could make the case that unobtainium was once aluminum. In other words, it was,
Exactly.
Very good point.
Right. Exactly.
Yeah, now we use it for cans. So it's hard to say what material science will go to, especially in regards to things like graphene and carbon. I mean, we don't have a full idea yet on just what we can do with stuff like that.
Right.
Now, I want to ask a question, and I want all three of you to answer this, and we'll start with James. Do you see a commercial use for hypersonic flight eventually? Will people be able to board a jet or something, get on a mass driver and get shot or whatever, and be able to New York to London in 5 minutes, something like that?
Another good question. I'm of the opinion that I think in certain cases, it's definitely feasible and applicable. But for the mass public, I think until a lot more infrastructure is put into place, and unless we find out some sort of different technology, I think it's probably not going to be used for mass transit. But in certain cases, as you said, maybe first class or business class, you need to get across the world very, very quickly. That is a very, very good way to do it. And I think we are definitely on the cusp of possibly seeing that, actually. So if you get on a rocket and you boost up, don't quite get to about low Earth orbit or LEO, and you go ahead and you dive back down and you cruise at that sweet spot in the stratosphere around 30 to 60 kilometers altitude, you can get to wherever you really want to go on Earth very, very quickly. Again, though, reusability is going to be a big, big driver of any sort of commercialization of hypersonic flight terrestrially.
Peter?
Yeah, I think erring on the side of positivity again, I think why not? We have Richard Branson and Jeff Bezos had gone to space. They paid for it themselves, right? And so I think James made a good point of like, yeah, if it's business class, first class, or whatever, the people that need to be there in that time frame, there are physical limitations that are currently challenging even for people who were flying Concorde, right? The pilots that were flying Concorde and things. But if we tackle some of the reusability of the materials, we really understand stable flight for hypersonic. I mean, yeah, I don't see why not. It couldn't go to commercial as long as it's, safe G forces for the passengers and all the like, right? Because if, again, I'm going to bring up Richard Branson and Jeff Bezos, I mean, they went to space, right? So effectively space. So it'd be, and to my knowledge, I don't think they had like flight training. I don't know. I could be wrong, but even then I'd like to be positive and think that, yeah, we'd be able to figure that out and at some point.
I would have never been able to predict that William Shatner would have actually went to space, but he did.
Very fitting.
Jonathan, your view of the future.
Right.
Yeah, I would stick more near term, right? And I would just reframe the question a little bit in terms of energy balance. And hypersonic flight, you're putting a heck of a lot of energy into heating up gas, right? Making hot air. That doesn't do anything for you. So I think you'd have to really try hard to try to make a compelling case that the time you save is worth all that extra energy. The area that might be more interesting would be, right, if we're, for air breathing hypersonics for entry into LEO, right? So you don't have to bring all your oxidizer up with you. That might be interesting. But for passenger jet around the world, I'm a bit more skeptical.
I guess it really comes to cost versus benefit. If somebody's willing, like the Concorde, if somebody's willing to pay the money, which for Concorde, it was mainly for the novelty of it. If somebody's willing to pay the money, the market will open up and it'll be there. But at the same time, it's still going to be far more economical for most people just to hop a Southwest flight, on a standard aircraft. But do you think that modern commercial aircraft could benefit from the research into hypersonics? In other words, can we make better subsonic planes through the research of hypersonics?
Yeah, it's a good question. It's a nice question. They're such different beasts, right? They're very different, right? When you think of the future of passenger jets, right, you think electrification. But when you think hypersonics, you don't have a generator on board, right, that you would have on your normal airplanes, right? So they're just so different. And then you think, okay, what are we really doing in hypersonics that's interesting? Materials and shapes. But those are very speed specific, and we don't worry about our typical airplanes melting.
quick aside, I think that the biggest thing for commercialized hypersonic flight, as Jonathan alluded to, is going to be your altitude that you can start, right? There's a lot of energy that we have to use in order to get up to that altitude. But feasibly, if you were to have, say, scramjet equipped hypersonic reentry vehicles. So maybe we have a whole bunch of those up on a space station in Leo or trips to and from the moon. You could re-enter with one of those vehicles, be at the perfect altitude to light your scramjet and then go anywhere you want once you're in the atmosphere.
I like that.
That could be a path forward.
Yeah, that's interesting. What other commercial uses, though, can you think of other than that hypersonics is going to allow us? And I don't want to really get into military use or anything like that, but civilian uses. It seems to me that you could, if you needed to move a document, all right, the president signs a document and needs to go to France, ASAP, something like that, that might there be an in there for hypersonic flight as far as a civilian use?
I mean, very, very fast delivery of material goods is always something that we strive for. I think the biggest issue with that is something that Peter touched on is the stability of flight and the mass production and safety of vehicles that are going to be leveraged. Obviously, they need to be relatively inexpensive if they're delivering things on the regular, and you need to make sure that whatever's in the vehicle survives once it's there. So recapture, landing is going to be an issue. Vibration in flight will be a big issue. Naturally, if you're going this fast, if you think turbulence in a passenger jet is bad, hypersonic flight is a brand new beast.
Don't fly over the Himalayas or the Rockies, because you fly into Denver airport, you're going to see some turbulence in just a regular commercial jet, and that's got to be so much worse when you're going at these speeds.
Yeah, and I kind of wanted to circle back to the question of hypersonics contributing to anything to the subsonic kind of bluff body type of flight. My mind couldn't help but go into things like Formula One, right? While a lot of Formula One research goes into there and then goes into certain commercial vehicles, right? That's been known. And so while I can't think of anything specific, I think just the sheer research going into hypersonics and just the offspring of techniques, while I can't think of an exact example, I think inevitably can definitely help improve any sort of subsonic, transonic, supersonic flight. It's just a means of having more data to really understand how things fly. And I think I couldn't help but my mind going into adopting different technologies from peak performance, pushing materials and things to their limits, like in Formula One, and then allowing those technologies to trickle down and eventually to commercial vehicles.
Yeah, I think towards that, we'll see a number of technologies, right, that are in development.
Right.
And this is purely speculative, that will come and improve humanity in general.
Spot on, yeah.
You see that in every case, right, of these kind of developmental programs.
Geometries of increasing speed in flight. Now, we have all kinds of things, especially built things in the past, from the Wright Flyer to the Apollo capsule reentry, that different geometries work differently in the atmosphere. So do you see that as we explore hypersonic flight, the geometries of what we think of as an aircraft are going to be very different in the future than what we see today?
Possibly, yeah. I think it really always depends on the objective, right? The capsule itself, it will always have kind of a larger surface area shape just by the nature of being able to slow down with a greater surface area. So they'll like to use more surface area to decelerate as you're entering, and then also choose a trajectory that is as slow as possible to reduce peak heating. So the general shape, I think, of something like a capsule, because its intention is to come back as in one piece with astronauts in it, that may be the same, but I think you'll see different variations that can achieve that. And then as we're talking about things that are, let's say, more commercial-esque or more streamlined, like a Concorde-esque shape, I think we will be seeing very drastically different shapes just because of different objectives. Like I can talk about things that I've seen on news articles of Quest. It's a quiet supersonic body that is much more needle-like shape out of NASA, and it's meant to have a low boom, right? So it's meant to be a quieter traversal than Concorde had, right? I think as people start incorporating their different main objectives, it will culminate into this pinnacle of a geometry that can tackle all of those things, fly more quietly, be reusable, and be that optimal shape for a given trajectory that it needs to fly to get from France and then back in no time.
Sonic booms. This was always a problem for Concorde, in addition to its extremely loud engine noise. I saw a Concorde take off back in the day at Charles de Gaulle Airport in Paris, and that was the loudest aircraft that I think I've ever heard, which it's now an antiquated aircraft that's out of service, but it was very loud. But then the sonic booms. So managing sonic booms, especially when you're going this fast, how hard is that, and what can you do to really mitigate it, and can you eliminate it?
Yeah, so that's a really good question. And so it's an active area of research, right? So the idea when these aircrafts are flying supersonic, so the actual noise source is starting to move faster than the noise itself. So it generates this interesting Mach cone shape. And so what they try to do is be able to manipulate the way the acoustics generate on the vehicle to then more so delay it and hope that there's also points of kind of abating that sound. And I don't know too many details other than that's what they're really trying to go after. And so they can also kind of look at the way the shocks come off. It's a whole study of being able to understand, can we manipulate the shock to, again, kind of abate that sound or dampen that sound? And so it is a whole game of acoustics that is possible, and people are actively studying that, which is really neat.
I think it's fascinating. The ultimate in hypersonic, all right? We already have hypersonic objects, natural ones, as meteorites coming in at great speed, like ridiculous speed. Some of them may even be so fast that they're hyperbolic and interstellar in origin. We don't know. So can you learn anything from looking at, for example, meteorite trajectories coming into the atmosphere? Can you learn anything about hypersonic flight by looking at nature itself?
Yeah, I think that's definitely something that we do on the daily, right? We definitely like to use things in nature that help us describe or help us take advantage of for our given objectives. Specifically with meteorites, I think one of the things that we observe mostly is just how it's able to survive a given trajectory that it's beaming down from the sky, right? And so those are some of the things that I take away. And then also understanding the material composition of the regolith. People have studied different porosities of the meteorites and things like that. So to understand, why did this one break up and why did this one not break up, right? So trying to leverage things from space definitely help guide us into further research.
Hypersonic flight in space exploration. Okay. Obviously, you can go extremely fast in space, but when you get to Mars, which we are going to explore Mars, and we're talking about space planes, putting an aircraft in the atmosphere of Titan and the copter on Mars. So do you see that there might be a use for hypersonics other than re-entry or entry into an atmosphere? Do you see that there might be a use for hypersonics in NASA's exploration of the solar system?
I would say, sure. Again, this is speculation, but if you want to move fast around a planet or a moon with an atmosphere, then hypersonics is a very good way to do it. The problem, or maybe not necessarily a problem, but the issue that is going to need to be studied is atmospheric composition. And when you're looking at the overall density of the atmosphere, that's going to change the criteria or the design criteria for whatever hypersonic vehicle you want to leverage. So, for example, Mars, at Mars's sea level or at ground level, the atmospheric density is roughly the equivalent of 30 kilometers altitude here on Earth, which just so happens to be right within the sweet spot of our hypersonic vehicles. But Mars is also very, very dusty. And when you're flying this fast, weather interactions with rain, ice, crystals, particles, even sand in the atmosphere really, really accelerate the ablative interaction when flying at these velocities. So you're, again, progressing with material sciences, understanding what that looks like, the recession rate, making sure it's uniform on these vehicles. That's going to be very much a challenge.
Peter, any views on this?
Yeah, I think James really hit the nail on the head, especially with the erosion criteria and with the dusty storms that Mars has. There's a lot of projects that my colleagues have worked on, and when I say colleagues, I'm referring to at the University of Minnesota, that has looked at entering into Mars, what that looks like. And then also they're exploring being able to land on different atmospheres and what that looks like. So yeah, I think some of those challenges that we have is really just getting through the atmosphere first. Because once you get there, I think I was talking to James about this last night. But the idea of discovery, while I don't want to speak for any NASA engineer, but I was under the impression that they were really impressed with how well their quadcopter could fly in that environment. I think some of the challenges, some of my main challenges and my colleagues' main challenges here at the university that we study is mostly just being able to enter these atmospheres safely and then also able to properly exit to return home.
Jonathan, any views on the future of space exploration involving hypersonic flight?
I think we've touched on them. I mean, we can get really speculative. It's challenging here. It's going to be very challenging far from home.
Yeah, remotely. Remotely flying an aircraft. That's bad enough just with the Mars copter. Imagine what you have to do to remotely operate a quadcopter on another planet with a delay of, 7 minutes, something like that on average, depending on where Mars is in its orbit. And it really lays down that our technology is getting really amazing. I mean, we couldn't have done this we certainly couldn't have done it 20 years ago. Now, James, I got a question for you. When you look back at the SR-71 and the crystal window and everything about it, does that give you a healthy respect for the engineers that designed that thing?
Oh, very much so. That's kind of a staple of, or one of the reasons why I actually wanted to be an engineer is you look at anything from the SR-71 all the way to the Saturn V rocket, you just kind of sit there with mouth agape and just in awe. It's really, really, really cool to look at and then also to understand how it works. It's just simply awe-inspiring.
And we did it in 100 years. Poor Orville Wright could probably never have imagined that within a century, we would be landing on the moon.
Very well said.
And I think about that a lot, that just how fast this happened, how exponentially fast that we developed technology. Now, granted, there were reasons for that drove it, but at the same time, it's almost an example of technology moving almost too fast because like I said, it took less than a century to get where we're talking now. Do you think that this represents a kind of analog of Moore's Law? In other words, do you think in 100 years we will see the same pace of technological development in aerospace that we have seen for the last century?
That's another really good question. I think as far as the rate, it's going to be entirely dependent on what drivers are involved. If people feel that there is a very high necessity and there's a lot of funding involved and interest for the progression of commercialized hypersonic flight or just hypersonic flights in general, I think we could and will see significant progress in that regime. Humans are very, very innovative, and I think we're nowhere close to our limits. So as long as there's an interest, I think the progression will definitely be there. Whether or not it's as fast is definitely up for debate. But I think the primary driver is going to be one of necessity.
Old materials. Now, I bring this up specifically because of SpaceX. They have decided to go with stainless steel with Starship. And stainless steel just has the right properties for that. So do you see that some materials in building aircraft and hypersonic aircraft never go obsolete?
Absolutely. There's certain materials that just do their job so well, and we've gotten to a point in our manufacturing processes where you can mass produce them reliably and within tolerance that I struggle to see any way they will ever be replaced. Will there be better materials that are developed in the future? Absolutely. Will we strive to make those mass produced and more readily available to everybody? Absolutely. But I think it's going to be really, really hard to displace something like stainless steel or aluminum.
Which is a good thing because, I mean, elements are elements. And we have a very clear idea of that. The question is, how do you mix them and make new alloys and things like that? How much room do you think's left in that? Do you think that in material science, metallurgy or plastics or whatever, have we gone down enough avenues to know what's possible in the future as far as building aircraft?
Oh man, I don't think so. I think that's why people dedicate their lives to this, is they think that they have some alloy composition and then you can literally change the constituents by mere percentages and get different results, right? So I think that there's there's a whole slew of things to be uncovered. And I think that's why material science is starting to see a huge boom in using artificial intelligence just to better find these parameters that they care about, to kind of have these objectives within their material design, like at the atomic level, because people are actually able to now kind of look at microstructure and do these nano architected materials. While that doesn't solve the production capability, I mean, that people still have so many parameters to go through. I mean, yeah, I think that that's going to take a long time before we can tie a bow on that and say, yeah, we've left every rock unturned.
Yeah, you start with the art of the small and then get to that point where you can manufacture some of the really, really cool properties that you find.
A bridge too far. All right, we've talked about Mars and its dust and flying hypersonically through its atmosphere and the challenges that would be presented there. But I've got a wild card, Venus. Do you think we could ever build a hypersonic craft that could actually ply the atmosphere of Venus?
It's another really good question. I admittedly do not know all that much about the atmosphere of Venus, other than the fact that we could theoretically create a floating city on Venus, and it would be at a relatively hospitable temperature. Wouldn't want to breathe it, but having hypersonics on Venus is definitely very intriguing and may be a really cool mode of transportation if we were to ever have create an establishment there.
Well, the interesting thing there is that Venus hosts, and this is why I brought it up, Venus hosts the most Earth-like environment in the solar system in its upper atmosphere. If you get about 50, I think it's about 50 kilometers above the surface, you actually would not die if your spacesuit got a hole in it, because the atmospheric pressure is about the same as Earth at that level. Obviously, it gets way worse the deeper you go, but at that level. So the question, I think, wouldn't be that could you put an aircraft in there, because the pressures are very similar. It's just, how do you deal with the hydrochloric acid and sulfuric acid and everything else that is present in the atmosphere that can degrade your spacecraft? But at the same time, I don't think anybody's really thinking very much about, other than the space that, the atmospheric cities and floating structures and things like that you can do hypothetically at Venus. I don't think anybody's really thinking about what we could do in exploration of it, other than life-finding experiments and things like that. Back to Jupiter. So putting a probe in Jupiter's atmosphere is not really on the radar right now, but that would seem to me, given the sheer size of that planet, that would seem to me to be automatically hypersonic, right? At least for that environment anyway, so that you could actually cover enough territory to even explore it. So hypersonics, as opposed in regards to exploring gas giants, to get back to that. Peter, what do you think?
Yeah, so I think that is still an area of study. I think NASA Ames has done research in the 70s, maybe around that time, looking at atmospheric entry into Jupiter. You have such a larger atmosphere, and then so the time it takes from entering the atmosphere to the surface is significantly longer than it is to Earth. So you have to sustain that trajectory or hypersonic environment for so much longer. So theoretically, you'd have to have this material that, either if we were to have the type of ablator that is actually, you're deteriorating your material, getting that heat dissipated away from your shuttle, or it might not be a shuttle, who knows, your capsule, you name it. That's going to be a very monumental task in itself. But you're beaming down there, and I think that there's a lot to uncover, things that people are still really interested in. I think that there must be, I know I have someone I know that's also working at the university thinking of Jovian atmosphere things. But yeah, I think that that's going to be a very active area just because of how awesome that planet is to be able to get data on.
Yeah. And the other really interesting point, too, is the challenge of sustained controlled flight in those environments. Obviously, it's going to have to be fully autonomous, and the wind speeds of the different layers and the storms on Jupiter are going to be a monumental challenge in order to maintain stable flight, let alone good enough to actually have instrumentation to gather data.
Artificial intelligence and the development of it and hypersonic flight. How do we incorporate AI into hypersonics?
Very good question. I think obviously any sort of flight control is going to be a no-brainer. When you're moving this quickly, having any sort of human piloting, while it could theoretically be feasible, I think leaving that to artificial intelligence would definitely be more feasible.
Yeah, and I think AI, I mentioned it used for helping scientists discover new materials and optimal materials for hypersonic flight, but also leveraging things that just help improve our processes of understanding physics and actually developing the capabilities to predict how a vehicle is going to behave. So we're talking about like whether we're flying in Mars or Jupiter, right? The atmospheric conditions are markedly different. I mean, even from Venus, right? So I think that if we can leverage artificial intelligence and machine learning to enhance our computational predictions and really gather a lot of good data, I think that would be indispensable for us to improve our ways of understanding and leveraging hypersonic flight.
Question for all three of you. What is it like to be actively working in the cutting edge of aerospace at Lockheed? James?
It's a dream come true. I love Lockheed as a company, and I've built a team around me where I'm constantly the dumbest person in the room. So it makes my life always interesting, and it's really just a fantastic opportunity that I would not ever give up.
Sir, do not deprive me of my title in this interview as the dumbest person in the room. I work very hard at that. Peter, what's it like?
Yeah, I absolutely love it. Coming into working every day on things that I'm truly passionate about, that's something that I'm very grateful for. And so being able to say also on top of that, I'm working on an area of research that is just full of different problems in physics. And, there's always something new, and different papers are being published, discovering new things of how hypersonic flow behaves around different geometries and things like that. Like it's just an amazing thing to wake up to every day. So and having the opportunity to do that for a career is something that I'll always be grateful for.
Jonathan?
Yeah, adding on to all of those things, working someplace like Lockheed on these really fun, hard problems is a blast. And what makes it really nice is that we always want to work on challenging problems, right? That's what we're physicists, we're scientists, we're engineers. That's what we thrive for. But being able to do that with exceptional people is not always easy. And someplace like Lockheed, right, that gives you that opportunity is fantastic. And then on top of that, has resources to bear, that you can apply to your problems is quite exceptional.
So the common theme is that solving problems is what drives you guys, right? Is that accurate?
Very much so. Yeah, we're all problem solvers by nature, and being at the cutting edge of solving these problems is what makes going to work easy every day.
Science and engineering, it's the most important thing we as humans do. Thank you, all three of you, for appearing with us today, and I hope to have further conversations, as things develop and we move further into the idea of hypersonic flight.
Thank you, sir.
Thank you.
It's been our pleasure.
Event Horizon and my channel are now available as a podcast on Apple Podcasts, Spotify, and YouTube memberships. Early ad-free episodes, bonus episodes, and sleep-focused content. Sign up now by clicking the links below to your platform of choice.